Hey everyone, thanks for coming out here for this tutorial. So Julia asked us to provide an overview of what is grid forming and what we'll be covering is how to model them, what they are, what kind of performance requirements can be specified for grid forming inverters, how to make it control agnostic, and so on. So my colleague Wenzong and I will be covering this over the next 3 hours. Hopefully we can cover all the content. As some of you may know, I do have a tendency to keep talking. So I'm not sure if we'll cover everything of the content, but we'll try our best. Yeah, I know. We're known for I also have some demos to run. I hope that runs. There's always Murphy's Law that might prevent it from running properly or something going wrong, but let's see how it goes. Brief introduction from myself. I've been with EPRI for a little bit more than 5 years now. I primarily work on our research projects that look at high inverter penetration, looking at modeling them, looking at analyzing them, both for small system studies and large system studies, both EMT domain and positive sequence domain, and not just from the bulk power system connected inverter side, resources side, but also from distributed energy resources, variable frequency drives, and so on. So power electronics, both on the source end and load end. I'm not a power electronics person. I'm more of a power systems person, but my work has been on applying them. Wenzong, want to quickly introduce yourself?
Yeah, hey everyone. My name is Wenzong Wang, and I'm also with EPRI. I've been with EPRI for like 3 years. And my area of research is more on the distribution side. So I do a lot of modeling and dynamic simulation for distributed connected DER. And in the grid forming area, one research that we are looking at is how you define the performance requirement for them in microgrid applications.
Thanks. Since we have quite a few people, probably we'll leave the introduction just for the breaks. There's a break in between where we can all meet around and we'll get started. So what we're going to cover today is essentially go towards in a staged manner, talking about what's the definition of grid forming, how do we specify requirements for grid forming, looking at some aspects from both transmission and distribution connected examples that we've been looking at. We've been doing work a little bit more on microgrid area to how to identify grid forming inverter requirements for microgrids, especially from a black start process. Trying to identify from a planning perspective, transmission planning perspective, how do you plan for the size of grid forming? Where do you plan to locate grid forming inverters? How can you decide if a new inverter that's coming into the system, a new inverter-based resource that's coming into the system should be grid forming or not, or it is beneficial to be grid forming or not? We'll touch upon some of those. And the content will revolve around providing similar examples from modeling across popular software that we all use. So I'm not going to spend too much time here because all of us here are probably aware of it, that how the power system has been transitioning, where earlier we had central station power plants and the flow of power was usually top to bottom from the generation station to the transmission down to distribution. But what has been happening is those central station power plants have been replaced by both transmission connected wind resources, transmission connected solar resources on the distribution system, both rooftop PV and maybe standalone resources as battery energy storage installations and so on. And what's essentially happened is now you have no longer a top-down flow of power, but you have flow of power in both directions. And that's changing the way we have to operate the system, is changing the way we understand how the system itself works and how we model the system and take into consideration all these various characteristics. And what's also changing is what we want from these inverter resources, the needs and the services that we want these inverter resources to provide. Now, a few pointers in this whole presentation, we'll be using the word or the acronym IBR for any inverter-based resource. That's going to signify anything connected both to the transmission network and distribution network. Some of you may have heard the acronym DER for distributed energy resource before. The reason why we are not using DER here is just for simplicity. So IBR can mean both in transmission connected and distribution connected inverter resource for the purpose of this, for the next 3 hours at least. And SG will be synchronous generator. So previously, when we had a system which was synchronous generator dominated, the goal was any inverter resource, the moment any disturbance occurs, trip and do not cause any other changes to the system. The intention was that the synchronous generator system, the existing mechanisms that are there, will help bring the system back or clear or recover after the fault and so on. And we didn't want inverters interfering with that operation. So essentially what all inverters would do was you would just inject active current and provide no other services at all. But as we have the system transitioning where we go to more increased penetration of inverter resources, we've started realizing that we want more services from these inverter resources. And you'll notice this theme throughout the presentation where we talk about services being provided from inverter resources, because the way we want to project for the future is revolve around how many services can we get from inverter resources and in what way can we procure those services and obtain those services. So the performance of an inverter-based resource is going to be governed around the services that it can provide. So as the system evolved and we had more inverter resources coming into the system, we wanted more services from the inverter resources, primarily things like closed loop voltage control, maybe closed loop frequency response. And note that these are capabilities. There's no reason that this capability will be used up, but the capability should be there. And for those who are familiar with, say, FERC Order 842 and 828, that brings about this capability to provide automatic voltage control, provide frequency response at the entire plant level. Now, these are traditionally a little bit slower types of response, especially when you look at a large solar plant or a large wind plant, where you have closed loop automatic voltage control or closed loop frequency response primarily at the plant control level, which then filters down to the inverter level, and then you get the services at the point of interconnection. But when you close the entire loop, you get this frequency response or you get the voltage response, but over a longer period of time. The other thing to consider here is the capability to provide frequency response doesn't mean that there is going to be headroom maintained on inverter resources, doesn't mean that there's going to be under frequency response provided, as long as the mechanism is there to provide that response when required. But most of the inverter resources would operate on maximum power point, and there would be no capability or headroom available to provide under frequency response. But once we started getting around these services, what we want to go in the future is make these services faster. We want to procure them at a shorter time scale. We want to procure them faster as soon as the disturbance occurs. We want to procure them without relying on synchronous generators. Now, this does not necessarily mean that we want the exact same service that a synchronous generator would have provided. The idealistic intent is not to replicate a synchronous generator, although we can, but inverters can do so much more than what a synchronous generator does. So potentially by replicating a synchronous generator, we might be missing out on capability that can be provided by the inverter resource. So for example, things like if you have something like a traditional electromechanical oscillation in your system, so a 0.8 hertz oscillation or a 1 hertz oscillation, which is because of the synchronous generator characteristics, with an inverter resource, if you try to replicate a synchronous generator, you might get the same kind of oscillatory behavior. But an inverter resource could potentially do much more than that. It can react faster, it can control itself faster, which could then mean in a future system that those oscillatory behavior may not exist, at least when you have lots of inverters in place. So we want to go along the path of procuring more services, procuring them faster, replacing the services that the synchronous generator would have provided. At the same time, trying not to replicate a synchronous generator itself. And some of these services could be things like fast frequency response, could be things like grid forming characteristic, could be aspects about maintaining more stability in the network. And how we define these services and how we define the time frame in which they are supposed to be delivered is what we want to go towards for a future network. So why is it a challenge for inverter resources to provide these services? I mean, we were talking about these services being provided, but from a fundamental perspective, from a very basic operation of an inverter, why is it such a challenge? So think of it in this way. So if you have a synchronous generator dominated system, let's assume this is a synchronous generator dominated system in this cartoon. And these blocks that you have here, let them represent the fact that it's not possible to move the system in an easy manner. So you have all this rotating machine, you have all the metal that's moving, you have whatever is inertia and so on. But let's represent that in a cartoon manner with these blocks here. So this system is not going to move around too much. Now in the system, when you have an inverter-based resource connected to it, and this inverter-based resource is injecting current, injecting power into the network. Now, any change in power injection from this inverter-based resource is not going to impact the system much. So the system is not going to move around when this injection of power from this inverter resource is going to change. But if the system itself moves, the inverter resource is going to move along with it, right? Because the size of the inverter-based resource firstly is smaller, and the synchronizing aspect between this inverter-based resource and the synchronous generator is tight. It's tightly coupled to the network. So when the network itself moves, this inverter-based resource is going to move along with it. This behavior has always occurred in a power system. This behavior has always been there since the first time, let's say, a wind turbine connected 2 decades back. We have never called it anything before until recently, where we have started labeling it as grid following. So this essentially what's happening here is that all that the inverter is going to do is it's going to position itself towards the newer position when the system itself moves. So if the system moves to a new voltage level, new angle level, the inverter-based resource is going to follow it, move itself along, and try to position itself relatively in the same manner so that it can keep injecting the same current. So it's, if you want to think of it in any other way, you have one person standing next to you, that person moves, you move along with it, keeping the same distance apart. Now, in a future system, when you have more inverter-based resources connected, or when you become an inverter-based resource dominated system, if we don't do anything else, so if we maintain the same way in which we control inverter-based resources, if we maintain the same way in which we interconnect inverter-based resources, if we don't do anything else, then firstly, what's going to happen is this network is going to start being able to move much quickly. So you no longer have those skids to prevent movement. So your network itself is going to be able to move quickly because very simplistically, there's no mechanical mass involved. So electrically, this network is going to move. The second thing is, now, if there is a change in current injection or power injection from this inverter-based resource, it's going to be able to move this system around. When this system moves, it's going to move the system again. And when this moves, it's going to move the system also. So now there is this closed loop relationship where both systems are influencing each other. Electrically, they are both going to influence each other's position. It's not going to be a scenario where the position of one resource electrically is fixed and it's only the other resource that's moving electrically, but they're going to influence each other. And in that closed loop relationship where they are going to be influencing each other, that closed loop relationship can become unstable when you have an inverter-based resource control. So this instability that can occur here because of this closed loop relationship is, of course, now dependent upon how this inverter-based resource control is and how the control of the other resources in the system also are, because they're going to be interacting with each other. Now, in a traditional inverter-based resource, these controls are fast, which means what's going to happen is if this is going to move around and that's going to influence the movement of this resource, this is going to try to track this movement very fast. It may fail in tracking the movement. Even if it doesn't fail, as it is trying to track that movement, it's going to influence the position of this system, which can cause an instability. The way I like to think of it is very simplistically, this was told to me by a controls professor back in school, is that you picture your finger moving in front of you, and you picture your finger moving slowly, and your eyes are supposed to track the movement of your finger. So your finger moving is equivalent to this entire network moving. Your eyes that track the movement of the finger is effective to this inverter-based resource trying to track the movement of the system. The signal that gets processed by your eyes and goes to your brain is what the inverter's control is doing to tell it that, okay, I know where that system is. You keep moving your fingers slowly, you can track your fingers movement very well, very fast without getting dizzy. You move your finger up and down very fast in front of your face, you will get dizzy. So moving your finger up and down very fast is equivalent to this system moving around so much that that another resource is unable to keep track of where the system is. It's trying its best to keep track of where the system is because it needs that in order to inject current into the network, but it's unable to do so because its control system is reacting much faster, and that can cause an entire unstable loop to come up. So that's the reason, one of the main reasons why there is a challenge for inverter-based resources to inject current or inject these services into the network. Now, of course, this is an extremely high-level way of talking about it. As you go into the weeds of control design and so on, there's a lot more stuff that can come up there. But at a very high level, from a conceptual perspective, this is one way to understand why it is so challenging for inverter-based resources to provide these services as you have more inverter-based resources connected to the network. So in this scenario, then grid forming inverters could be a solution. Now, what exactly then is a grid forming inverter, and what does it do, and how does it help provide the stability is something that we'll talk about. So now let's talk about what's the definition of a grid forming inverter. Now, some of you may have seen these kind of diagrams before, wherein a grid following inverter is represented as a controlled current source, and a grid forming inverter is represented as a voltage source, so voltage behind an impedance, right? And what gets implied from this diagram is that, so this is from an electrical perspective, think of this as a Norton equivalent, this is a Thevenin equivalent, but this impedance is large, which means that this is the only current that's going into the network, whereas here the impedance is small, so which means there is decoupling that's there, which you can have more current injected into the network when a disturbance occurs. But along with this representation, there are aspects, and this is of course high level. If I dig into this more deeper, there are nuances involved, but from a high level perspective, you might have heard these statements that grid following inverters are current sources. And if there is a network with only current sources, it cannot operate. And hence we want to go towards a voltage source. Now, at that high level, yes, that statement is true, it is valid, and so on. But if we dig a little bit deeper into this, any inverter resource that's connected to the system today is a voltage source inverter. So every inverter in a solar plant is a voltage source inverter. Every inverter in a battery installation in a wind power plant and so on is a voltage source inverter. Current source inverters are used, may not be used too much today. If at all they're used, they're probably used in motor drive applications where you have a current source inverter driving the motor. So it's more on the load side. So the reason why a voltage source inverter is treated as a current source is because of how it strictly controls its current or tries to control its current when a disturbance occurs. So which means that if you don't change the amount of current being injected into the network, or you treat that current injection to be nearly constant in the few instances after a disturbance occurs, then that's what gives it its name as a current source. But Kirchhoff's current law still exists in a system with all current sources. Kirchhoff's law doesn't vanish when you have only current sources. Ohm's law doesn't vanish when you have only current sources. So which means from a fundamental circuit theory perspective, a network with all current sources has a valid solution. It has a valid operating point, and it has a valid mathematical solution that can be attained, provided that these values of these currents can be changed in a timely manner in order to make the system stable. So if you think about it from this perspective about what will happen, supposing you have a disturbance that occurs in the system, supposing you have a change in load in the network, then if you don't change the amount of current that's being injected, if you keep these values of ID and IQ constant, then yes, you can get a network collapse. Because the amount of current that you're injecting into the network, the voltage that gets generated in the network is a function of the amount of current being injected and the load and the impedance in the network. So if you don't inject enough current, there's a chance that your voltage will collapse. However, if you do have some control that can change these currents in a timely manner, then you can have this network to be stable, right? So if this control, whatever happens, the way this control works, whatever it does, right? The goal here is to not try to prescribe what this control should be in its internal framework. The goal is to try to prescribe what the control should do from a performance perspective. Because if we try to start prescribing what this control is internally, then we run the risk of in some way being restrictive with respect to the type of control architecture that can come into the network. So if we can make this control change the amount of current that is being injected into this network and change that current in a timely manner, then this network can be stable even after you have a disturbance in the system. So if this is possible, then we can rethink the way we have to define grid forming. We can rethink the way we think about grid forming. Yes, there's one aspect about current source and voltage source, but that's not that may not be the only differentiating aspect between the way a grid following inverter and a grid forming inverter works. It can be differentiated by the type of service that it provides and the way in which it changes its current injection into the network. And this is just a simulation example where that same network where you have 3 current sources, and you increase the load in the network, but by changing the way in which you inject that current, you can pick up that load, you can survive that load disturbance, you can maintain frequency, and so on. How you design that control or the objectives of that control now become important. So what that control is asked to do, what kind of quantities is it asked to control in order to change that amount of current injection is going to now become important. And that's where it plays a role in defining grid forming behavior. So if we now have to take that perspective where what we are essentially going to be looking at is, supposing you have resources that have all that you want to prescribe is the way in which you will change that control, or the way in which you will change the objective of that control while still keeping the performance-based respect that you want, and while still keeping the fact that all that you want is current to be injected into the system, not thinking about whether it's a voltage source or a current source. Let's see what happens when you look at few certain scenarios. So if we now consider, let's go back and let's say we consider a synchronous machine. So let's consider a synchronous machine. And we all know how a synchronous machine control system is structured, right? So you have a machine and you have a governor system, which basically controls the way mechanical power flows from the turbine to the generator, and it controls speed, and it has an excitation system. So what the excitation system does is you have basically something which is providing a voltage to the DC field winding of the machine. And that voltage which is provided to the DC field winding, the rotor rotates inside the machine, you generate an AC sinusoidal wave. Now, what the excitation system is doing is it's trying to change that excitation, the DC field excitation, based upon the terminal voltage of the machine. Now, how many of us think that a synchronous machine is a grid forming device? Why? Okay, so what will happen if we make that machine not control voltage? So supposing we have either constant excitation control. So let's say we don't have an exciter as we know it. We don't have static excitation. So a lot of static excitation schemes will look at the terminal voltage, they will rectify it, and then they'll feed the DC exciter. And those machines, they cannot self-start unless there's some residual flux in the core of the machine. But let's say we remove that static excitation and we put constant field excitation. So whatever happens on the terminal side, we will not change the DC excitation voltage. Will that machine still be grid forming?
Yeah.
Why?
It's like a voltage source behind your feeding. So if the grid voltage dropped, more reactive power would naturally flow out of the machine.
And so it will remain stable as short circuit strength reduces.
Maybe up to a point. I don't know.
Okay, so let's see what happens. So I have three types of excitation control represented here, right? And when I say three types of excitation control, only one is a true excitation system control. It's two others are fictitious in a way. So first type of excitation control is going to be that we're not going to have this exciter in place. And instead what we're going to have is we're just going to have constant field excitation into this machine. The second type of excitation control that we're going to do is we're going to create our own excitation control loop, wherein instead of trying to control the terminal voltage of this machine, we're going to try to control the reactive power to a certain value. So we're going to make this machine behave in a way such that whatever happens on the grid, it's going to try and maintain its reactive power to this value of 13 megawatt. That is the pre-disturbance operating point for the system. And the third excitation control is going to be our traditional voltage control, which we have for an exciter. So depending upon how we set this up, so now let's select the excitation system to be 1, right? So now this is going to be constant field excitation. And and all that the network is it's just going to be a change in, so you just have a fixed infinite source and the machine is going to be injecting power from here into the network and you have a fixed source. Let's not worry about the step changes that are there. They're going to be disabled for now. All that the thing is, what's going to happen is you're going to change the SCR. So you're going to change the short circuit strength at this point. Now, there are many ways in which you can change SCR. There are many ways in which you can define whether you want to make this infinite bus voltage, keep it at 1 per unit, or you want to keep it from a perspective of only having maintaining 1 per unit at this terminal and so on. In this exercise, we're going to keep this voltage of the infinite bus as 1 per unit. So if we run the simulation now, and hopefully it runs as I think it's supposed to run. So we expect that up to a certain point, as you said, that yeah, the machine will be able to tolerate change in short circuit strength, and also that the reactive power out of the machine is going to increase as the short circuit strength drops, and the system is going to be stable. Now, there is a fine point here which I'll come across that we have to think about, wherein it depends upon whether we are looking at it from a short-term voltage stability perspective or a long-term voltage stability perspective. We'll come to that, but there's a reason why we are looking at this particular exercise. As this runs, I'll just plot the results here so that we can see what happens. I mean, there is, because it'll take some time to run. So essentially, we're going to wait for the machine to come to steady state. We are going to then change the short circuit strength, and we're going to see what happens. Now, one of the main things we want to keep in mind here is that the resource also has a governor control enabled in it, which means that it has some frequency control put into it in order to, as the system speed or as this machine speed changes, it's going to change its mechanical power output and so on. Now let's see which comes up first. And we're going to repeat the same exercise with an inverter-based resource. So what we're going to do with an inverter-based resource is we're going to repeat the same thing, wherein here we talked about the machine having these three types of excitation, right? Wherein you have constant field voltage, you have constant Q control as an exciter, and you have constant V control as an excitation system. We will replicate that with inverter-based resource. So as the simulation is running in the background, this is the response for the same set of runs which I had done previously. So if you have constant excitation control, which is this blue curve, as the short circuit strength reduces, yes, in this initial 2-cycle time frame, things are stable, but as you progress, you start becoming unstable. As you move towards Q control on the machine side, again, you start having an instability, and this instability starts occurring much faster. But as you move to your traditional V control for your machine, you are able to tolerate the change in short circuit strength. Now, granted that this has nothing to do with the 2 cycles, but what it gives us a picture of is if you can survive these 2 cycles, or even if you survive these 2 cycles with your voltage behind impedance, there is a further chance of instability, which is intuitive. There's nothing new here that we are talking about. We all know about how voltage stability is, and the fact that if you have to transfer power across an impedance, you need to be able to maintain voltage and so on. But it speaks to us the fact that if you have something like Q control, even if you are able to ride through the initial few cycles of disturbance, there is no guarantee of stability later on. Now, if we transfer this to an inverter-based resource system, wherein traditionally what inverter-based resources, or the way inverter-based resources are structured, yeah, and this is the simulation running. So traditionally, the way inverter-based resources are structured is you have essentially, you have a plant controller which looks at the point of interconnection, and you have a plant controller trying to maintain closed loop voltage control at the point of interconnection. But that controller is slow. What the plant controller does is it sends active power commands and reactive power commands down to each inverter. So at the inverter level, each inverter is operating on closed loop active power control and closed loop reactive power control. So now, if the plant controller is slow and you don't have that voltage control, at that inverter level, since it is on active power control and reactive power control, when you have a change in short circuit strength, when you have a change in phase angle, there can be an increased chance of instability occurring. And all our traditional grid following inverters, they work with that active power control and reactive power control at the inverter level. Because the job of maintaining voltage, the job of maintaining frequency, or controlling voltage and controlling frequency, or providing voltage response and providing frequency response, is at the plant level is slower. So when you have a system where you have more of these resources which are doing at the inverter level, if they are doing reactive power control, then you start seeing instability. Here again, there's, in some way, it is still riding through the first 2 cycles. And this is actually a traditional type of inverter control that we have today on our system. There's nothing new in this inverter control that we're talking about. We have not yet progressed to the newer forms of grid forming control that have come up to the system, or come up in research literature, and some manufacturers have products. This is the same traditional type of inverter control that we have. We're still able to ride through the first few cycles. And of course, the type of instability that manifests is completely different, because there's no rotor mechanical mass, there's no electromechanical time constants, everything is electrical. But conceptually, when you have Q control at the inverter level, when you try to force the inverter to control the amount of Q, even though it might have a slow reset voltage control through the plant controller, you are increasing the chances of instability that might come up as you have lower short circuit strength. But when you move to fast voltage control at the inverter level, and we'll show you later on that some of the new grid forming concepts, essentially what they are doing is fast voltage control, if you dig into how the controls are structured. So conceptually, if we move to fast voltage control at the inverter level, then you still have the same response that you see in those first few cycles, but then you're able to maintain a stable behavior. And if we now compare the response of a machine and two types of grid forming control, if you now compare the response of a machine and two types of grid forming control, wherein essentially both types of grid forming control, they're structured in vastly different ways. One of those types, you still have the capability to operate in what we may call as a grid following mode, where you are controlling P and Q. But if you change that to voltage control, and you have another type of grid forming control, which does implicitly in it, when you structure the grid forming control loops, and we'll talk about some of them in the next few slides, implicitly in it, there is a way of voltage control embedded into that control. So if we look at it from the perspective that what the inverter is actually doing is it's shifting from being Q control to V control, that can be one pathway in which to start bringing in grid forming behavior without only specifying voltage behind impedance, but you're rather specifying the performance or the service that you want from the inverter. So if you specify just voltage behind impedance, as we saw in the synchronous machine case, if it's just a voltage source behind an impedance, but if you try to change that in a way where you're controlling Q, you can still become unstable. So just specifying voltage source behind impedance is not a sufficient condition for grid forming. What you might need to have more than that is that you need to go down to specifying fast voltage control at the inverter level instead of having fast Q control. So now if we compare what's happening with three different types of resources, wherein you have, I don't know if you can make out the colors very well, but if you have the blue is the synchronous machine with voltage control, the red or orange, in my screen it is orange, here it's probably reddish. So that's one type of grid forming control with fast voltage control. And the green is another type of grid forming control with fast voltage control, is that they do have slightly different characteristics in this time frame, but overall they're all able to maintain the response that's needed. Yeah.
So on one of your earlier slides, you showed grid forming versus non-grid forming. Non-grid forming or grid following had a phase lock loop.
Mm-hmm.
But if you're performing fast voltage control, doesn't exclude having a phase lock loop. I'm a little bit confused because there are certain like manufacturers of wind turbines that they have a fast voltage control of the terminals of the wind turbine. And then they have a slower plant control. It's a hierarchical PI control. And though they seem quite stable under a wide variety of grid situations, I'm not sure I would call that grid forming. I couldn't establish its own synchronism, for example, or operating under very low short circuit ratio.
So there, in a way, it comes down to controller tuning also. And it also comes down to the type of operating condition that we're going to be looking at. So what you said is extremely true and fully correct, that some of these resources, it may not be able to establish its own voltage under no load condition. But there are ways to do that. Even if you have a phase lock loop, there are ways to do that in order to generate your own voltage under no load condition. One of the things here is that the types of control that do not use a phase lock loop, they are also not necessarily always stable under all conditions. So then it comes down to good control design across both types of control mechanisms. Now, the aim of this exercise is not to try to portray one type of control against another. What we want to establish here is that the manufacturer can choose to decide how they want to implement grid forming control. In terms of the fact that if the manufacturer chooses to implement a PLL, it should be up to them. They should be allowed to do it, as long as they can showcase that over a wide range of scenarios, their control is stable and can provide the services that are required. So we have done some black start studies with PLL inverters, and it's the PLL it's critically part of the synchronization loop. It comes down to how you handle the auxiliary load that's there in the plant. It comes down to how you handle the frequency response control loop. So there is an element of tuning involved there. And as I said, the aim here is not to say that a PLL-based inverter will be able to do everything, and we only want PLL-based inverters. We definitely want all types of control to come into the system. The aim is that we don't want to exclude any type of control if the manufacturer can showcase that they can provide the service that is required. So if we want a grid forming definition or a grid forming map that will not be dependent on specific control elements inside the control, that it shouldn't be that if certain control element exists, the resource is not grid forming. It should be that if that resource is able to showcase the service that is needed and provide the service that is needed, then it can be considered grid forming.
Okay. But your example here, you contrasted a fast voltage control versus non-fast voltage control.
No, in this way, in this example, both these have, in a way, fast voltage control in them.
Yeah, well, I meant the previous.
Yeah, okay, yeah.
Yeah, or the one that went unstable. So that's, I guess what you're saying, that's an example of one approach that could have grid forming characteristics, but that's not the only approach. That's fast voltage control isn't necessarily an objective.
No, fast voltage control is an objective of grid forming.
Okay.
So having fast voltage control is the objective of grid forming.
Okay. One objective.
Yeah, one objective. Of course, there's frequency control and short circuit current and all of that, which we'll have to get to, but one of the objectives is fast voltage control.
You're saying that it's a necessary objective.
Yeah.
So going back to like a synchronous machine, a synchronous power plant, you tend to consider inherently grid forming. Without the exciter control, it's a constant source. It doesn't have fast voltage control. And so what you showed earlier was that is not actually grid forming, because it eventually goes unstable for a large step in grid impedance.
Yeah, it may remain grid forming in those small few cycles, but if you look at it, and if your intention of grid forming is only to look at those small 2 cycles, then it's okay. But if the intention of grid forming is from an overall system stability perspective, wherein trying to improve the stability in a weak region of the network, trying to maintain the stability when the last synchronous machine trips, trying to provide adequate frequency response, trying to provide adequate voltage control, if we want all of that, and if we want, let's think that synchronous machine was an inverter, right? So if we want to continue to operate 100% inverter system where we need grid forming resources, so if we have all of that as our perspective on grid forming, then that machine wouldn't classify as grid forming.
So what made that synchronous machine a grid forming machine was not only the fact that it's inherently a voltage source behind impedance, but also that it had the excitation system. And probably later when we talk about power, it also has the inertia.
Exactly. So if we recognize it from that perspective, and then we translate that to an inverter, we can then change this into a service-based requirement where we have, or we want grid forming inverter-based resources to also have fast voltage control, fast frequency response, and so on at the inverter level, rather than saying that a grid forming inverter consists of control elements XYZ or doesn't consist of control elements ABC. Nick?
I just wanted to put a little bit of a philosophical point that helps maybe a comment on this, right? So a lot of this conversation, and I know you don't mean this, but a lot of this conversation is sort of bully, stable, not, right? And that's industry sort of needs, how stable is it?
Yeah.
Right? So the fixed excitation system isn't like inverted pendulum unstable for most perturbations that handle something small. So as we progress, and this isn't a criticism, but it's just thinking, as an industry, we have to have a better handle on, so the fixed excitation synchronous machine has got a pretty small stability window, whatever, the potential energy boundary.
Yeah.
Pick whatever.
Yeah.
It's not zero,
Yeah.
it's not the inverted pendulum, right? These other ones, the window gets bigger in different directions. And as an industry, we kind of, you're talking about what service do you need? So it's like, I can translate that into how stable does it need to be? What are you trying to accomplish? So you gave an example, having worked with a company that had the inverter that you're talking about. And those are grids, you know, there've been examples where those wind plants have tripped to islands where there was load, that they were within the attraction of that system, and they ran for extended periods of time.
Yeah.
You know, if that ain't grid forming, what is it? Well, the answer is, that's not really what we meant, right? You can't start it from and they wouldn't have been stable if something had come along a little bigger than a wind turbine. They would have knocked off. So we need to constantly be pinching ourselves to not sort of use this bullying, is it or isn't it, and what do we need?
Yeah.
And I know you're saying that.
Yeah. Absolutely.
And as an industry, you know, the utility, the planners and stuff need that insight, both as what they're asking for equipment and as they're operating their system. How close to the brink am I?
Correct. Yeah.
And what's it going to look like when I get to the brink? You know, it's not black and white. I'm, you know, Columbus sailing.
Yeah.
Okay. No,
Absolutely. Jason, you had a point?
I was going to say basically what Nick said, you know, talking about the different aspects and flavors of grid forming for the services. You know, there's certain cases about what do you do to keep the control stable in a weak network, a low SCR network, as opposed to a zero SCR network, a black start, as opposed to providing inertia. All those things are somewhat separate and independent when you look at the control algorithms, but they all have to work together.
Yeah.
So the set of services, I think, is where you're going, is to say, what problem am I trying to solve and what specific control mechanisms allow us to do that?
Exactly. Yeah.
Coordinate together.
We probably covered all of this. So essentially what we've noticed in a lot of our work is that the PLL is not the sole reason for instability to come up. It forms an integral part because it's part of the entire control structure, but there are other dominating factors that come into play which might make it become unstable. And we have some of that results later on. And what this also means is that it doesn't mean that if there is a PLL, it cannot operate in 100% grid. It comes down to how it is tuned. It comes down to what kind of design is taken place. It comes down to what kind of control objective is put in place. It comes down to what kind of system it's operating in. And they will all start interacting with each other in a way to determine whether there's different layers of stability or whether they're working together or not. So what this helps us do then is it helps us define a performance-based approach to define what grid forming is or what grid forming should be. Wherein essentially, we can say that a grid forming inverter is an inverter that can at minimum do these many different kinds of characteristics, wherein it can operate with and without synchronous machines. In other words, it can operate stably once the last synchronous machine has tripped, and it can operate stably when connected in parallel with a synchronous machine. So it should be able to do both. It can operate stably when connected in parallel or alongside other inverters in the system. It has to positively contribute to both load and generation balancing, positively contribute to voltage control, work towards improving the system stability, have robust fault right-through, and so on. At the same time, doing all this while respecting the equipment limits. we kind of expect a grid forming inverter to provide 6 per unit current if it's not been designed for it. So 6 per unit fault current. So even if an inverter is designed to be something like a virtual synchronous generator, we can't automatically expect 6 per unit fault current to come out of that inverter unless it's been designed for it. So while respecting the equipment limits that are put in place, now, yes, you can probably design that inverter to provide that, and then the equipment limit for that inverter becomes 6 per unit or so on. So be able to provide all of these services while respecting the equipment limits and while also meeting our metrics that we have today related to stability, security, and reliability. Some of this might be not tripping UFLS relays or something like that. Now, it's a different question that maybe those metrics that we have today have to change. Maybe as we go towards a system which has more inverter-based resources, things like maybe what we have today is we think that if there's fast roke-off, if there's going to be frequency moving very fast, our inherent understanding of the system can lead us to think that there's a power system separation going on, or there is a generator going out of sync, or something like that. Because in a synchronous machine system, we are used to frequency moving slowly, and when frequency moves fast, we think that there is a disturbance occurring, there's a system separation occurring, there's some machine going out of sync. However, and that has defined one of the metrics that we have for things like UFLS not tripping, or things like how we define the roke-off thresholds and so on. However, as we move to a fully inverter system, maybe that fast movement of frequency is okay. Maybe that there is no actual power system separation going on. Maybe the power swing is fine as we move towards a system with more inverters as things are moving fast. So it's a possibility that we might change these metrics as the system evolves, but whatever is the metric at that point in time, the inverter is expected to meet that. Last point is that in the way we have defined this, we don't think that every grid forming inverter should be a black start resource. Every black start resource should be every black start inverter or black start capable inverter should be a grid forming inverter. But every grid forming inverter need not be a black start resource. In the same way as today, not every synchronous machine plant is a black start capable plant. There are only few designated black start. When I say few, I don't mean few as in 1 or 2, but there are certain synchronous machine plants that are designated to be black start capable units. So in the same way, we have to have a differentiation and classification of grid forming inverters, wherein every inverter resource that's capable of black start is by default a grid forming inverter, but every grid forming inverter need not be a black start capable inverter. And what that will do is that will help transition the input, or it'll help bring in grid forming technology maybe faster to the system, because black start capability, being able to provide inrush currents, being able to provide motor starting currents, being able to take care of faults in that environment where the system is extremely weak, is still not well known for inverter resources. But however, being able to stabilize a local pocket of the system, being able to survive the last synchronous machine trip is probably more well developed. So having this differentiation between black start capable and not black start capable for grid forming resources can change the way in which we get grid forming resources into the system, where we can start getting grid forming resources faster into the network if we have this differentiation between black start capability and not. So now we'll talk about few grid forming control methods that have been proposed in research work, that have been there, and some manufacturers have it. We are not saying that these are the only ways to do it. There are so many more different ways of doing this, but this is some of the ways in which they are. So, Wenzong, want to take that?
Just use this.
Does it work?
Yeah, it should. All right, can I get the pointer? All right. Excuse me. So now let's look at a few of the grid forming methods that has been proposed in the literature. Okay. All right. So here we just listed a few of them. Of course, there are more that have been proposed, and there are more that's been proposed right now. But these are several of the common ones that, when we talk about grid forming, that people normally think of these several types of controls. So the first one is that we all know virtual synchronous machine. And the second one is matching control. So what these two control do is they try to emulate synchronous machine dynamic behavior. And the difference between them is the first one implement the synchronous machine swing equations and voltage control equations solely on the AC control of the inverter. And the second one, which is the matching control, tries to leverage some of the DC side dynamics to emulate the swing equation of the synchronous machine. But in a sense, both of these two types of controls, they try to emulate synchronous machine and its dynamic behavior. And of course, this doesn't mean that they act exactly the same as a synchronous machine. And like Deepak mentioned, inverters have more flexibility. And as a matter of fact, these type of inverter controls, they can actually do more than synchronous machine. For example, the inertia of these type of inverter controls or the damping can actually change because they are not bound to some physical constraints. Now, the next two types of controls are both droop-based. Now, the difference between them is the first one is what I think more of you are familiar of the first one, which measures the terminal voltage and current, which is the P and Q. And based on this PQ and the droop curves, it determines the internal voltage and frequency of the inverter. So the inverter is controlled as a voltage controlled inverter. The voltage and frequency of that internal voltage depends on the terminal measured P and Q. So this forms a closed loop droop control. Now, this type of droop control is more similar to what we have today. And it's also what Deepak just showcased, one of the control there, which still use a PLL. And instead of measuring the grid P and Q, it measures the grid frequency and voltage. And based on this frequency and voltage, it calculates the P and Q for the inverter to track. Now the difference between, excuse me. So the difference between this one and a traditional grid following inverter that we use today is that this P and Q signal gets updated fast based on the terminal voltage and frequency measurement instead of trying to keep a fixed P and Q at the fast time scale. And we will look into the comparison between these two types of droop controls later on in the following slides. Now, if you look at the first four types of different control mechanisms, they're all phasor domain controller, which means they look at phasor quantities. So they measure the P and Q from the grid. They look at voltage and frequency, which are in the phasor domain. Now, when we move on to this last type of grid forming control that we survey here, is called virtual oscillator control, which is basically a nonlinear type of control that is look at the time domain measurement. And the benefit of doing it time domain instead of phasor domain is that it avoids the measurement of phasor, so it can have faster dynamics. Now, as we can see, there are all these different types of controls being proposed. So now the question is, do they have similar behaviors? Now we first, just as an example, we first want to look at two types of droop controls that we illustrated on the previous slide, and to see whether they have, oh, excuse me, no, it's better. Now to see if they have similar steady state behavior first of all, and then we'll move on to compare their dynamic performance to see whether they have similar dynamic performance. Now, in terms of steady state operation, this first type of droop control, like I mentioned before, it measures the voltage and the current at the terminal and calculates the P and Q, and then determines the internal voltage and frequency output of the inverter. But in a sense, what it does is to follow this droop curve. So when you have a load increase in the system, it will sense the active power increase from the inverter terminal, And because of this active power increase, it will then reduce the frequency of its internal voltage. And by reducing this frequency, it will let other resources in the grid know that, okay, my frequency is reducing, so you need to pick up more power as well. So by this mechanism, as we can see, if we have two of them in this example, they manage to share the increase in the load between them, and by reaching a new steady state frequency, which is the same across the system. Now we can have a different way to implement this droop control, which instead of measuring this P and Q, we can measure the voltage and frequency at the motor terminal, and then determine the P and Q injection from the inverters, which were illustrated in the previous slide. So by doing it this way, again, it can sense when the load increases in the system, it has a synchronization mechanism, and the frequency of this inverter will then drop. So in this particular scenario, this frequency drop will be caused by the PLL. And because of this frequency drop, it then knows to increase its active power generation to pick up the load. And at the same time, if you have multiple machines or multiple inverters in this scenario, in the system, they will again share the load based on these two droop curves. So as we can see, in terms of steady state operation, both of these two types of controls, what they do is to follow this droop curve, and at the new steady state, they will manage to reach the same frequency with the active power increase property shared between them. So there's no difference in terms of steady state performance. Now, when we go to the dynamic performance, Deepak will then compare how they look in the transient time frame.
Yeah, wondering, what causes the frequency to drop as the load increases with this whole, like, it doesn't drive?
Yeah.
Why does the frequency drop with the power increase?
Good question. And there are certain cases where the frequency won't drop, but it will rise also. The dependency of frequency to load change in an all inverter system is still a topic of research, because we don't know whether it will hold the same connotation, the same behavior in a 100% inverter system as opposed to machine. So in a machine system, the rotational frequency of the machine links to the electrical frequency of the network, and then it links to, let's say, the load, right? And then when you have a change in disturbance, you have a flux change and so on. In a electrical system or all inverter system, essentially what's going to be changing is the phase angles of the network. So when a disturbance occurs, what's going to happen is electrically, the phase angle of the network will change at different points of the system. And whether that phase angle change gets reflected as a drop in frequency at the inverter terminal will in some ways also depend upon what are the other devices that are there in the network. So if you have, let's say, a fax device, a series fax device, so let's say a UPFC or an IPFC as a series fax device, or if you have a phase shifter, which a phase shifter won't work in the time frame of a transient, it's more of a slower steady state. But let's say if you have a fax device in the network, which can change the phase angle properties of the network, there are certain instances where the frequency wouldn't necessarily drop.
But thinking from the electronics point of view, so single inverter driving load, then in that case, the only fundamental sense of frequency in that system is the crystal oscillator underlying the oscillator inverter.
Yeah.
Right. So, like, how do you get any sense of frequency? Right?
Yeah, so it just ultimately comes down to how the phase angle changes. Now, mostly or most of the time, the phase angle, as you have an increase in load, because the load is also electrically connected, or maybe there is some constant electrical characteristic for it, you will see a phase angle reduction, which will cause a frequency drop. But that characteristic also changes if the load characteristic changes. Now, if you have power electronic load, if you have variable efficient drives coming into the system, and the characteristics of the power electronic load is also serving its own objective, and the way the phase angle changes is still something as a topic of research. We've seen few cases wherein you have, let's say, a 90% inverter system and let's say 1 or 2 machines left in the system. And if you apply a 3-phase fault, the rotor speed of the machine decreases and doesn't increase. So usually when you have a 3-phase fault, you would see the rotor speed increasing because of the electrical power reducing and so on. We've seen certain cases where the rotor speed of the machine decreases instead of increasing. Does it really manifest in a generality? We don't know that yet, but yeah, that's something which is still open.
Deepak, you want? Yeah, I just want to add a little bit there. So try to make it simpler. So if you think about single machine with a load, and if we know for grid forming control, if they say it emulates the synchronous machine, right, then we all know what caused the frequency to drop, right? Now, if it's droop control, it's actually similar, right? So you see the power output increase, then based on droop, it will drop the frequency. Now, the interesting thing then is how a PLL-based control, for example, what Deepak showed, it's still like an improved version of the PLL grid following control that we have today. If we put that single inverter in a system, in an island with a load, now the load increase, does the PLL gives you the signal by reducing the frequency? Now that part to me is the most interesting, and based on our research at EPRI, we actually showed that PLL is able to sense that load increase by dropping frequency as well. So yeah, I think that's the interesting part, and it depends on the control lot.
So if we now take the basis that we've had so far, and we keep our focus on the initial transient and subtransient time frame, and pretty much I know transient and subtransient doesn't occupy 60 seconds, but let's say 60 seconds after a disturbance, then the way we can think of classifying, at least from a services point of view, without looking at it from a control point of view, is that at the inverter level, and why I'm stressing inverter level more and more is because when you have a wind installation, when you have a PV installation, you have so many inverters in the plant, and then there's that hierarchical plant control. Our focus is at that inverter level, at that turbine level. So at that inverter or turbine level, a traditional grid following resource would be something where P and Q are kept constant. So the primary objective of that inverter-based control is to control P and Q. Now, P and Q might slowly change over time based upon how the plant controller decides to change it. That's a slow variation. But in that transient time frame, the objective is to change P and Q, or control P and Q. What could be an intermediate grid following inverter is something which has P change as a function of omega, but Q is still constant. Now, this can be slow frequency response provided by the plant controller. And then what could be the possibility of grid forming behavior is that both P and Q change as a function of omega and V. Now, this is of course, at the terminal, when you're looking at it from the output of the inverter, right? It's not looking at the exact control law inside the inverter, but we're looking at the output of the inverter, that if omega drops, P reference will change fast or increase. If V drops, Q reference will change fast or increase. So when looking at it from the terminal of the inverter, essentially what's happening is you have both frequency control and voltage control implemented at that inverter level. And where this classification helps is it then helps making or develop control agnostic requirements for grid forming inverters. That what's behind this is grid forming inverters. So now let's look at it conceptually. So as I'd mentioned before, that and I promise you this is probably 1 out of 2 slides that have block diagrams. There's no other slide that has this kind of diagrams in this tutorial. But it's important, wherein if you look at it, let's say from 2 perspectives. So you have a virtual oscillator, which as Wenzong showed is more of a nonlinear time domain based characteristic or time domain based grid forming inverter. And you have on the right hand side a PLL based system, which a PLL is a phase lock loop as we know it, but in control system terminology, a PLL is also an oscillator. It's a voltage controlled oscillator. So based upon how the voltage is, we can control the oscillation. Now, both these control loops, and this is where some of the aspects about black start, as you had mentioned, of with PLL inverters and so on, we can actually make a PLL based inverter generate a sinusoidal wave. Now, both of these controls if you look at the virtual oscillator on the left-hand side, essentially what it has embedded in it, as I said before, was that these new forms of grid forming control have embedded in it a form of voltage controller. And the way you can make that out is there's a V reference signal coming in here. That V reference signal goes here and here. So you have V reference square. And that gets, or from that, you subtract V alpha square and you subtract V beta square. So think of alpha and beta for don't worry about the exact subscripts here, but think of alpha beta as a rectangular complex algebraic number, right? So x plus jy. Now, if you have a complex number x plus jy, the magnitude of that complex number is x square plus y square, square root of that. The square of the magnitude is x square plus y square. So V alpha square plus V beta square is the square of the voltage magnitude. You're subtracting the square of the voltage magnitude from a voltage reference square. That is a voltage controller. Because if you look at, let's say, a synchronous machine excitation system control, it has V reference minus terminal voltage magnitude feeding the excitation system. So embedded, and of course, after that, you have an omega generator, you have an integrator, and so on to generate the angle. That's how the virtual oscillator works. But embedded inside the virtual oscillator is a voltage controller, or embedded inside the, yeah. So this is one form of grid forming control. And with this, you can generate a sinusoidal voltage wave of any angle and frequency that you want. Now, if you move to the right-hand side, what's on the top here is a traditional PLL. Let's for now ignore what's at the bottom, right? So let's not worry about this portion for now. What's on the top is a traditional synchronous reference frame PLL. So the way a synchronous reference frame PLL works is you take in voltage. Let's either call it ABC voltage or rotating alpha beta frame voltage. It's a sinusoidal voltage. You take voltage as an input, sinusoidal voltage as an input. And let's say, for example, since we are for now neglecting this bottom portion, let's just assume that these quantities here are going to be fixed quantities. So you take in sinusoidal voltage as an input. Based upon an angle, you generate what's called a DQ frame voltage. So a DQ frame voltage is a DC voltage wave whose frame is aligned with the angle of this alpha beta frame. Okay. The aim of a PLL is to usually make one of these voltages zero. And if you make one of the voltages zero, your angle is aligned with the angle of your sinusoidal wave. That's how a PLL works. So you take one of those components of voltage, you feed it through a proportional integral controller, and you generate an angle. Now, if you have only this portion on top, wherein you are dependent on some voltage coming in order to generate an angle such that the rest of your control works, this definitely cannot work in a system that has no other voltage in it, because you need this voltage to come up. But if we look at it from the concept that we said that one of the properties of grid forming is to have fast voltage control at the inverter level. If you look at it from the fact that a virtual oscillator also has inbuilt in it a voltage controller embedded in it. So now if we make use of that, and if we add a voltage controller to a PLL, so you have again V reference square, you subtract from it V alpha square, V beta square. You have another controller, this any controller, and VD, if the PLL works well, if VQ goes to 0, VD is going to be the voltage magnitude. So you have VD coming in, you have some control effort added to it to generate a new waveform, and you close the loop. If you have this setup, so you add a voltage controller to a PLL, you can generate a sinusoidal wave from this setup at the same angle as you have a voltage oscillator, a virtual oscillator. So a PLL-based system with fast voltage control added onto it can generate a sinusoidal wave on its own, the same way as a virtual oscillator generates a sinusoidal wave. It's all about how you manipulate the control. And it's because of this that we are going down towards this fact of grid forming control to not have this perspective of only certain control elements are allowed to be there. Because there are so many different ways, and this by far is not the most robustly designed control. I'm I have designed this. So it's not by far the most robust control. There are many ways to make this more robust. There are many ways to even add on to this. But fundamentally, recognizing the fact that there is embedded in a lot of the other grid forming control topologies, embedded in it is a voltage controller. If we take that principle, and this is only from voltage, you can also have a frequency droop controller added onto it and so on, which we'll show later on, where this is a very idealized way of looking at it, because we are not looking at the current controllers, we are not looking at any of the other switching and so on. But this way of representing gives us a perspective of what is needed or what can be done from a services point of view. And so if we add this voltage controller to this, you can generate a sinusoidal wave of similar magnitude, similar frequency, and so on. And now if we take that, yes, no, yeah, Nick, sure.
It's for my EPRI. It's really E squared.
Yeah.
So
It's
not linear, and maybe the first approximation, it has sort of effectively a built-in extra gain of 2, if I insist on linearity.
Yeah.
Is that all right?
Yeah.
It strikes me that for large signals, maybe we're asking for yet another mechanism.
Oh yeah, I mean, for getting for good fault right through and so on, there are other stuff you have to add to this to make it stable for good fault right through. Yeah, that's it. Yeah, absolutely, yeah. So if we take the same concept and now we put it into an inverter, we put it with all the current control loops, we put it with all the DC side regulation that we have, and we put it into a system, and we test it. And this was tested against one of the criteria that AEMO has for their model acceptance tests. So AEMO has a list of model acceptance tests that they do. So this was one of the criteria that they had, and we just ran this one test where you have a pre-fault short circuit ratio of 3, a post-fault short circuit ratio of 1, an X/R ratio of 14, and we apply a 3-phase fault for 0.43 seconds at the inverter terminal. And since the controls are not optimally tuned, so there's the goal is not to compare like which control is better or which control had an infinitesimal increase in rise time and so on. The goal is to compare the fact that the controls responded in a similar trend or similar manner for this severe test. So all 4 grid forming methods now can showcase a similar response, showcase a similar behavior for the same kind of test that's applied. If we look at it from the principle that at the end of the day, what they're doing is they're doing fast voltage control and fast frequency control at the inverter level. And if we start applying those principles in, let's say, our interconnection requirements or in characterizing what should be grid forming, then we can allow for many different types of control to be developed by manufacturers without putting down restrictions on specific control elements to be applied. So the goal of this exercise was just to show that, firstly, many different grid forming characters or types have similar behavior, similar characteristics. And this is for a severe event, right? They have similar characteristics even for small signal events. So if you have just a load change or if you have a slight change in voltage and so on, they have similar characteristics even for that. But even for large signal events, provided, of course, you have added elements added to the control loop to ensure robust fault right through. And both grid forming and grid following need that. You need to have ways to ensure that you don't saturate your controls, you don't have wind up in your controls. You need to have ways in which maybe you need to freeze certain parts of your control. But provided you have all of that embedded and incorporated, then even for large signal events, they show similar behavior. Now, we don't know yet if these types of grid forming control will show similar behavior for all types of events. That's still an open research question. But we do know that for a subset of events, a subset of systems that we have tested out, they do show similar characteristics, which means that we can develop performance agnostic or control agnostic performance requirements. And there are examples around the world where this has already started being developed. So Hawaii has some, National Grid UK has some, there's a little bit in Australia also. So there are examples around the world where this has already started, and we need to keep going down that path without focusing on what's inside the inverter. We spoke about this. So now we'll talk about some practical use cases that we have seen both around the world and in some of our research work where we have applied it on some of the utility members with whom we have worked with on application of some of these controls in real systems in understanding how they would behave. I think we can. Wenzong, is this yours?
We'll start by talking about some real world applications of the grid forming inverters in the system, both in the distribution and transmission systems. I know in the audience here today, a lot of you guys from transmission, but actually, in my opinion, up to now, more grid forming inverters has been considered or has been applied in inverter-based microgrid design in the transmission, in the distribution area. And there are also some applications in transmission systems with low fault current and also with low rotational inertia. And this is today. In the future, what we envision is that we will have a lot more grid forming inverters deployed, both in the transmission and distribution grids to support reliable operation with low grid strength. And of course, we need to maintain stable and reliable coordination between all those numerous inverters and also with other devices in the grid. Now let's look at some examples of grid forming installations first in utility level microgrids. So I will talk about the definition of utility level microgrids later on, but in a nutshell, what it means is we have different scales of microgrid in the distribution area. And when we say a utility level microgrid, normally it refers to a microgrid that has a portion of the medium voltage feeder instead of just a single household. And for these types of microgrids, we have seen some projects where they use, it's very common today that they use a large battery energy storage system with grid forming capability as the master of that microgrid. And as the first example, we have this Mykonos microgrid in Florida, where they have a section of a medium voltage feeder with around 8 megawatt battery energy storage systems to support the town and nearby areas during grid outage. Now, this is basically the topology of this microgrid. And as we can see, the substation is down there. Now, instead of using the entire or forming the microgrid as the entire feeder, what it does, it has a islanding switch somewhere in the middle of that medium voltage feeder. And when there's grid outage, it opened that islanding switch, and then the energy storage there will then support the microgrid operation of the remaining part of the feeder. And we also have other similar microgrid projects going on. So here I show one in National Grid, New York, and another one in Canada. Both of them are in process. Now for the first one, this one is a bit larger in terms of in the scale of distribution, right? So the battery energy storage system is 20 megawatt, 40 megawatt hour. Now this one is large because it does not, it not only support one feeder or one substation, but instead it tries to support 5 substations. It also includes part of the sub-transmission, 46 kV line, and 10 feeders that are connected to those 5 substations. Now, as we can see, the common feature is they both use this battery energy storage system as the energy resource to power up that microgrid. Now, in this last example here, similarly, they have a section of the medium voltage feeder as the microgrid, and they have, in this case, both a battery system as well as a utility scale PV plant in the same microgrid. Now, we also have a few more examples of grid forming installations around the world, and Deepak, you will talk about them more.
So a lot of this, actually the next couple of slides are from Julia's presentation that she had in 2020 on grid forming installations around the world. I'm sure there are probably a little bit more since Julia presented this. So maybe we can have Julia make the next presentation on, again, installations around the world. But here again, there's a battery in the St. Eustatius Island where essentially it's both solar plus storage. There's seamless transfer between loss of the generator sets that were there even at peak load. There's several parallel grid forming units. There's no communication across them, so they pretty much operate in a seamless manner. There is a wind farm in Scotland which has been looking at doing black start with wind, essentially trying to understand if you have grid forming capability in wind energy systems. Can you do black start? Can you really energize a cable? Can you energize the diesel generator, which is located further away from there? Can you energize the load, and so on? So, and there are some examples also in Australia where there are battery energy storage systems which have been able to provide different kinds of response when there have been grid events. So grid forming inverter technology is definitely present in the system already and is operating, as I've mentioned. So there is these two battery energy storage systems in Australia where they essentially have been shown to respond to under frequency events in a manner which is required for the grid, and trying to provide the fast frequency response into the system, provide the injection into the network, and really help towards stabilization of the network in that local region. So when we talk about weak grids now, coming at it from a transmission system perspective, we spoke about how there can be pockets of the system that are weak. We spoke about how there are scenarios where you can have grid forming inverters which do not have black start capability, but are still able to support the system in a certain region, help improve the stability of a certain region. So there are multiple ways in which you can define weak grids around, and there are different characteristics of a weak grid. The way we will be defining weak grid here is from the simple electrical perspective. If you take any source, let's not worry about right now whether it's an inverter-based resource or whether it's a synchronous machine resource. If you take any source which is injecting some amount of active and reactive power into the network through an impedance into the larger system here, then very simplistically, as the impedance value increases, as you have, let's say, a longer transmission line, as you have the source being electrically decoupled from the rest of the network, then as this impedance increases, the sensitivity of this voltage to current injection increases. So this is going back to the cartoon figure that we had in the initial slides, wherein the system or the voltage starts moving around faster or more when you compare it to the injection of current. So the small changes in this current injection will cause larger changes in this voltage as this impedance starts increasing, because there's nothing to hold that voltage down. If you think of it from a very simplistically Ohm's law perspective, the voltage that is generated at this point is a product of this current and this impedance. So if this impedance is large and you have a small change in this current, you will have a large change in the voltage because the product is going to be large. So you're going to have I times L or I times X, the way you want to call it. And if X is large, a small change in I will still have a impactful change on the voltage. So you have an increased sensitivity of this voltage to current injection, which is one of the ways in which we can classify weak grids. There are other ways to classify weak grids, wherein you just have low short circuit MVA. Now, low short circuit MVA is not always necessarily related to having a large value of impedance here physically. So think of a scenario wherein you have, let's say, a system which has very high short circuit MVA, high short circuit current capability, but you have a long transmission line. Then you have low short circuit MVA at this point because you're not able to get fault current to this place. You can have another scenario where you still have a small value of this X, but you have a resource here that has very low short circuit capability. Even in that scenario, you have low short circuit capability at this point. So having low short circuit MVA does not, in an inverter based resource system, a weak grid from a perspective of low short circuit MVA is not always necessarily a long transmission line. It can also be related to the fact that you have a very electrically closed system, but all the resources in that electrically closed network are not able to provide short circuit current. So as a result, you will still have low short circuit MVA here. And the kind of instability that might arise in that system can be very different from the kind of instability that can arise when you have a long transmission network, because the interactions are different. So the initiating factor may still be the same, that there is low short circuit current, but the type of interactions that can occur can be extremely different. The other way to characterize a weak grid is a system which has high rate of change of frequency. So you don't have enough. So these first 2 points are probably more related to reactive power injection, reactive current injection, voltage control, and so on. This point is more from an active current, active power injection perspective, wherein you don't have enough active power injection, you don't have fast current injection, fast active current injection, and as a result, you have a larger drop off of frequency with respect to time. All of these together can be classified as weak grid depending upon the kind of scenario that we are looking at. This has been studied before. There are instances before from a synchronous machine world. So weak grid is not new. It's not new to inverter-based resources. Think of it where you have hydropower plants in the mountains and they have to transfer power to load centers through long transmission lines. There have been weak grid scenarios there, reduction in synchronizing torque, reduction in damping torque, wherein we then had to have power system stabilizers developed in order to improve damping and so on. So some of those concepts can actually be translated to the inverter-based resource world also, where you have concepts like power oscillation dampers being brought into play. But with power oscillation dampers, it becomes a little bit more tricky because you can have power oscillation damping both with respect to active current and reactive current, and trying to determine the priority, trying to determine which type of current injection is going to be important is crucial. Active current power oscillation damping has other associated impacts related to the type of resource which is being controlled and so on. So aspects related to weak grid, essentially what we want to say is it's not necessarily new. The concept has existed, but it probably becomes more challenging with inverter-based resources because of the way the controls work. And as we showed in the introductory slides, just looking at how the inverter-based resource control is going to continuously try to track the position of the grid and so on. And one of the examples around the world, I don't know what happened to the figure, but one of the examples around the world is both in the Texas power system and in Australia, where there are pockets of inverter-based resources far away from load centers and having to ship power through those long transmission lines, shipping power to load centers located far away, where that could be one place where grid forming inverters can help stabilize the portion of the network and help stabilize that pocket without having to think about black start capability, without having to think about whether it's needing to run a 100% inverter system or not. It's more about keeping that small pocket of the system stable. Now, one thing we want to put here is that although the tutorial topic is grid forming inverters, we're talking about grid forming inverters, it's not a silver bullet solution. So we shouldn't consider grid forming inverters to be the only solution or the solution that will help fix all problems. There are a wide variety of solutions that we can start thinking about when there are more inverter-based resources in the system. And in some way or form, they have to actually work together, right? There have to be a mix of solutions that we think about. Things like strengthening the transmission lines, retuning control loops, reimagining the way in which controls are done, looking at synchronous condenser operation, and so on. Each of them have their pros and cons. There's, again, none of these solutions are going to be one solution that will fit all scenarios or a one-size-fits-all solution. But in a way, as our grid transitions, we need to start looking at all of these solutions together in order to be able to get more and more different types of services from these resources. Where we're going with this is that when you start looking at a transmission system study, when you start looking at an example where you have a transmission network with a variety of devices, a variety of topologies, then you really need to call upon these different solutions in order to really help make the system stable. So think about an example here wherein it is a fictitious example based upon a real system. So we had a portion of the North American Eastern Interconnect, and we took a portion of that Eastern Interconnect, and we essentially increased the number of inverter-based resources in that pocket. So originally, there are wind plant connections in that system, and we increased the number of inverter-based resources in that pocket with adding more PV plants into that system. And then to make the system a little bit more, to showcase the fact that you're going to have long power transfers, you might start having resources located far away from load and you have to transfer power, constructed a fictitious 300-mile long transmission line to a load center located right on the top here. Now, we're going to ship 100 megawatts of power from where you have only inverter-based resources, and there's a little bit of load here, but primarily inverter-based resources, where you have a pocket of inverter-based resources, and we're going to ship the power all the way up here. Now, the goal of the study is firstly to try to understand if we can stabilize the system with having grid-forming inverters in this section of the network, or we need to have grid-forming inverters here also. The second goal of the study, or objective of the study, is to understand how many of these resources need to be grid-forming in order to stabilize the network. The third objective of the study is to understand, can we represent or model them in different simulation domains and different planning domains in order to plan the system with this kind of power transfer. And fourthly, of course, can a 100% inverter system operate, right? So as I said, we have inverter-based resources here. We have a bit of STATCOM located here and here in order to provide voltage control, and we're going to ship the power here. Few scenarios that we considered, wherein we assume that all the wind plants don't have any kind of plant controller in it. They don't have any kind of frequency response enabled. They are just providing injection of active power and reactive power, almost like traditional grid following plants. So all of them operate on maximum power. Now for the PV plants, we assume that all of them have local frequency control. We assume that they have some amount of headroom available. So they are dispatched and they're not operating on maximum power. For whatever reason, let's assume that they want to participate in a market to provide frequency response. So they are operating at that dispatch level. So our main set of resources to provide the grid forming capability is going to be the PV plants. The STATCOMs are not grid forming in any way, but they are providing fast voltage control by default, because that's what the STATCOM will do. So in some ways, it may have some grid forming property enabled in it, because it is providing fast voltage control, both here at the sending end of the transmission line, and there was another one at the receiving end of the transmission line. So now looking at the different scenarios, we started looking at what if we have only 1 out of 8 PV plants grid forming, then we increase if we have 4 out of 8 PV plants grid forming, and then if we have all 8 PV plants grid forming. So is there going to be a consistent improvement in performance across this? Is there going to be, after a point, only an incremental improvement in performance? Is it going to saturate? Is there some point in the network where you can clearly go from having very less grid forming to sufficient amount of grid forming, and any more after that provides incremental performance, is what we wanted to look at. So the first thing we did was just have a load increase in the network. So small enough disturbance in the system. And again, this is all 100% inverter, and we are shipping power to a load center far away, right? So there's a long radial connection also involved in this network. So the kind of instability that you start seeing is not traditional full-blown instability that you would see. Like you see, for example, here, if you have a load increase of 7% in the network, on the face of it, things start looking stable. But as you keep running the simulation for more time, you start seeing instabilities crop up when you have only one plant being grid forming. So this is not sufficient enough to maintain stability in the network. As you increase the amount of grid forming inverters, so as you go from scenario 1 to 2 to 3, where 2 has more grid forming inverters than 1, 3 has more grid forming inverters than 2, you start being stable in the network. And after a point, any increase in grid forming inverters provides only incremental improvement. So there is a point in which you go from having very less amount of grid forming to sufficient grid forming, but after a point, you won't get any more benefit for that system. Now, this doesn't mean that you stop having grid forming inverters or stop getting the capability to provide fast voltage control and fast frequency control. What it means is that as the system evolves, you will have to have more resources coming in. Yeah. In this, PV is providing. So the PV has headroom in it. It has both active power and reactive power headroom enabled in it. So it's not operating at maximum power point. So the PV inverter is providing grid forming. There's no, for this case, there was no additional battery energy storage implemented.
So it's operating on the right side of the.
Yes. Yeah.
Deepak, you start to see any rules of thumb?
Rule?
Any rules of thumb come out of this?
Not yet. No. No 70-30% rules of thumb yet. Actually, the point on that 70-30% rules of thumb, I'm deviating from this, but it's good to deviate. We found that depends a lot on how you represent load. What kind of load characteristics do you use? Do you have static load versus motor load? Do you have three-phase induction motor load versus single-phase induction motor load? Do you have distribution connected resources? Those rules of thumb vary so much depending upon the type of load, which is now making it more challenging to define a rule of thumb. So, okay, yeah. So question was, is there an importance in the sequence in which we are adding them? There is. Not in this, but there is a case that we have later where depending upon where you add them and depending upon what rating you have and how the other resources in the system are added after that. Yes.
Are these resources like the same size of PV?
No, they're not the same size. They are varying in size. Yeah. Yeah.
Can you comment on, you said up to a certain point it helps, then no longer helps. Can you comment on the mechanism, why that happens?
So it comes down to this varying degrees of stability, right? So once you go from there's insufficient amount of voltage control, insufficient amount of frequency control, your system collapses. Once you have that sufficient level of voltage control and frequency control, it's not that there is no additional benefit. There is a small incremental benefit coming up, but it's after a point, there's only so much more voltage control will do because you already have system firming capability brought in, which means that the system is stable or the system has enough capability to respond and react. So any additional capability, all that it does is it distributes the burden amongst each individual resource. So from an efficiency perspective, you are probably more efficient because each resource is contributing lesser to what kind of burden it's required to uptake and undertake. But from a overall system point of view, you don't see any additional improvement. Yeah. Yeah. So and we actually just mixed them all over. So in all these studies that we do, we start taking random combinations of the grid forming capability because we've seen that they have similar performance across the various kind of contingencies that we have. And we also want to try to see if there are different types of grid forming in the same system, will they interact with each other? Now, there are cases where they start interacting with each other. But yeah, in this, it was just randomly mixed.
You mentioned about having grid forming inverters at the generator side and at the other side of the long transmission line. Can you comment on the difference between when we should put it on each side?
So it's a little bit there intuitive. And why I'm saying it's intuitive is that if you have only load here, and if you have all your voltage control only at this point, these inverters are going to be controlling voltage only based upon local information that they have here. And if you're going to ship power here and if you have nothing to control voltage here, then the voltage can fall down here. So it's not, in this kind of scenario, it's not about can you put either or, you have to put on both sides because otherwise you'll have nothing to control voltage on this end. So And you may not need frequency control on this end. So in this case, we didn't have any frequency control on this end, on the resources here. So all the frequency response is being provided only from here. Now, there is other set of research work that we have been doing to showcase that it does matter where you put frequency control also. Because depending upon where you put frequency control, you can have stable or unstable responses, especially fast frequency control. But in this case, we had all the frequency control here, but for voltage control, you need to have it on both sides, because there's only so much. Even if you have a long transmission line, there's some amount of charging current that will be provided by the long transmission line to provide maybe some voltage rise. But after a point, there's only so much that it can do. Yes. Yeah.
Yeah, because you have a starter comp there, so can you comment on what is that starter? In this case, the starter comp where you use
It does reduce the need to a certain extent, because the STATCOM is providing some amount of voltage control and reactive power capability there and providing voltage support there. But it doesn't reduce the need for any frequency response capability from grid forming inverters, because the STATCOM that we have considered here does not have any supercapacitor or anything like that. So it's just doing just general voltage control. Nilesh?
Just listening to some of the comments, would it be fair to say that the number of grid forming devices, capacity and the location is large?
Yes.
Like it's hard to say the volume of the necessary to work as well.
Exactly. Exactly. Systems. Mhm.
Could it be really complicated? Right?
Yeah.
Come up with a rule of thumb.
Yeah. So it's system specific, it's load characteristic specific, it dependent upon the other elements that are there in the system. So it depends upon that too. Inverter specific from what perspective? Oh yeah, yeah. Yes. Yeah. And after a point, it may not matter. But until you reach that point, there is a there is a sequential impact on the next step that you put. So if you put a grid forming in step 1, there's going to be an impact in step 2. If you don't put it in step 1, then the grid forming inverter you might need in step 2 may be more than what you need in step 1, and so on. Yes. Sorry. No, go ahead.
Where I'm coming from is that the component would come with a grid forming technology that I want 100 megawatt of grid forming device at this location. It will not be that amount of application.
Yes.
Somewhere else, but the component say, okay, I'm coming with this. I'm going to install this. So that's where I'm coming from. That maybe you go with grid forming rather than grid following.
Yeah. So the benefit that it might provide at that location may not be the benefit that you want from the system. So that will play a role. Yes. Yeah.
just thinking about rules of thumb. If you don't want to right now, you say it's larger than 0.
Definitely larger than 0. Non-zero. Yeah. Yeah. Yeah, absolutely. There may not be an incentive right now because there's no additional, I hate to say this, but market mechanism associated with it. I'll refrain from commenting on that, Andrew. I have no idea. I'll have, if there's any manufacturer or OEM in the room who can comment on that.
Is it something you can modify after the fact, that it's just a controller, it's software?
Some inverters and some manufacturers do have the capability to have an over-the-air software update. If there is the associated energy capability available, so let's say like a battery installation, right? If you have a battery, some inverters have the capability to have an update to change from grid following to grid forming, because provided you have the same limitation on maximum current, you have the same limitation on that kind of an capability curve envelope, then you can change it, but it depends upon them having the capability to do it. Yes.
So we do also have a business from the solutions for Microgrid, where we sell about the requirements also. So in these cases, I think a lot of the manufacturers, they are already offer the capability on their inverter, but I mean, from the solution perspective, how we provide the service or the solution, the customer requires the engineer specific only function or Microgrid function. So that is already
Yes.
From the perspective of Veterans Campus, some of them might have been. If we define the farming inverter, the inverter that is able to provide the loop on top of voltage, provide gas power, frequency active, all of our inverters are good on our side. And it's just a matter of how fast.
Yeah.
we do that.
Yeah, it's a matter of how fast. Yeah.
So, like, it's not on the discussion how much reforming, but what reforming you are. There's another point in this triangle, like the speed. Speed reforming before, and you have to figure the balance. Probably this is what the rule of thumb will start to show up. Right.
Yes, Nick last, and then we'll move on.
Yeah, sorry.
No, it's fine.
My insistence on rules of thumb, so I could just practice a conversation. Cartoon-like simplicity. Amps equal dollars. So all the other stuff is detail. So you have grid forming functionality that actually drives the current rating up. So virtual synchronous machine with a super good rating. Otherwise, yeah. Second, just to reinforce it on the outside, I can say it. Back up and just do it. For batteries.
Yeah.
Manufacturers know how to do it. Folks have seen pictures of me when I didn't have any gray hair, standing in front of a grid forming battery system. Built in 1995. We know how to do it. Just do it.
Every manufacturer knows how to do it, because that's how it has been done. They always have first in the kind of tests like this. But the inverter manufacturers are lacking the system in it, so they don't have the unit to make something. Some another layer.
Yeah, but while absolutely true, people selling crap that don't understand the market that they're selling it to and the application for which the crap they're selling is used deserve to either be driven out of the market or get their back to it. Just excuse, oh, we don't know what you want. We don't know, we don't understand this stuff. We're going to sell you the same crap that we've been making. I'm sorry, that's not going to move us forward. That will something.
Yeah. Yes.
One more comment. Since we talk about the added cost, if the scenario is like we only need to revise the control without the hardware inverter switching device upgrade, I think that cost should be manageable. I'm not from manufacturer side, but I can imagine that. Then change the grid code can fit that. but like Nick said, if the change is switching device upgrade from 1 per unit to 3 per unit or even higher, that's a different story.
Yeah.
So from just my understanding, now the question is, will revising the market incentive or scheme more complicated than the technology we are talking about here? Probably yes. And the one of the reasons I'm here is I want to get some information like knowing a lot of features of a grid forming inverter and the benefits. What is the limitation of the different design of a grid forming converter? Like I said earlier, just revising the existing controls software of the existing installation versus it's a fundamentally different hardware structure, higher rating, and class control. And what's the implication to the developer and the transmission owner and system operator? Then we can think about what's appropriate approach to revise the grid code, asking them to do it, or put some reasonable incentive there to make it happen. And that's part of the information I'm very, very glad to get from here. Thank you.
Absolutely. So just moving on in this, we not just load disturbance, but just looking at three-phase faults, seeing that if you don't have grid forming, how the network behaves, and if you start having grid forming, then the type of robust fault right through, of course, with the added aspects of robust fault right through behavior that we spoke about earlier, and not just the fault on the local network itself, but fault even on the long transmission line. So disrupting 1,000 megawatts of power from flowing and then getting that 1,000 megawatts back up, the grid forming inverters are able to keep the system stable. Wenzong, you want to take that from the distribution side also?
Yeah. So in the following, I guess 3 slides, I just want to show whether similar stability issues or challenges can happen in future distribution grids as well as what we see now or more trending in the transmission network. So for that purpose, we study this example distribution feeder where we have 2 distribution feeders connected through this substation transformer to a representative of transmission system, which is a Thevenin equivalent. And the disturbance that we study is we apply a voltage sag on this voltage source here, which basically represents a fault in the transmission system that gets cleared in 0.1 second far away from this substation because we still have 55% remaining voltage. And what we also tested is different short circuit ratios at this substation distribution substation. Now, in today's standard, commonly what we see at the distribution substation in terms of short circuit ratio is more on the scale of 50 or above. So it's strong. Now, in future, what could happen is if this distribution feeder or substation is connected to a weak transmission area, then what could happen is the distribution feeder can get even weaker compared to the transmission. Now, given that there are larger amount of inverter-based resources connected on those feeders. And on this feeder, we have, as we can see, these 2 feeders, they are actually identical. So on each of them, we have 3 PV plants, utility scale PV plants. And for PV 4 and 6, and similarly for 1 and 3, we always use this conventional inverter with volt-var control. So I call this conventional, but actually it's actually not there today because volt-var is required by 1547 2018, and that certified inverter has not come to the market yet. But I call it conventional compared to more futuristic grid forming control. Now, for these 2 plants in the middle, we tried both conventional as well as grid forming control, and we'll see the difference in the response. Now I'll go over the 2 types of controls that we used. For the conventional control, the idea here, the main difference between all of these are more on the reactive power control part. So for the conventional control, we use volt var. And for those of you that are not familiar with volt var, it's basically a very slow droop type of control where you measure the voltage and then try to adjust the reactive power of the inverter output. Now, like I said, it's very slow on a time scale between 1 second to 90 seconds, and that's required by 1547. Now, as comparison, we have these two types of control. The first one is droop-based inverter control, and I'll not go over it again. The second one is basically the same as this conventional control. The only difference is now instead of using volt var, we have a what we call dynamic voltage support or fast reactive current injection, which basically controls its terminal voltage in a fast manner. Now, if you look at the results, we can see that if we use this conventional control, and right after 2 seconds where the voltage sag occurs, then it starts to have that huge deviation in voltage, active power, reactive power. And when the fault is cleared, it did not return to the previous operating condition, but instead it shows all this oscillation behavior that we also see in transmission networks in when the system gets weaker. Of course, this only occurs with SCR equals to 5, whereas if the SCR is 50, as is common today, we don't see this kind of issue with the grid following inverter as well, because simply the grid is strong enough, or the transmission network or the substation is strong enough to support this distribution feeders that we don't need that fast voltage support from the IBRs connected in the distribution. But in the future, things may change. As the transmission gets weaker and the whole grid gets weaker, we also expect that the IBRs connected in the distribution will share some burden in regulating the system voltage. All right, we'll skip that for sure. And yeah, for the next part, I'll talk about the performance requirements for grid forming inverters for microgrid applications. Now, all that we have shown up to now basically shows that we can, or we have the potential to define performance requirements for grid forming inverters. And this is not only for microgrid applications, but also for transmission connected, distribution connected, based on performance rather than specific control. But such a definition is lacking in today's world. Now that's what we are trying to do to come up with some performance requirements. And because my area is in the microgrid, in the distribution, so we focus on microgrid first. Now, yeah.
So sorry, my question is, I think you may have contradicted yourself, or maybe you haven't. So the title, because the minute I saw the title, I was going to ask the question, does this apply to everything? And then you sort of answered that. So could the title of this be, performance requirements for, regardless of microgrids? Because the title seems to indicate it's only for microgrids, but yet you sort of said that it may apply to everything. Can you just clarify that before you go on?
Okay, yeah, certainly I will need to. So when I say it applies to everything, what I mean is the way that we can define grid forming performance based on performance rather than specific control, that applies to everything. What I'm going to present here are specific to microgrid. And right now it's still hard to say whether these will apply to transmission connected. Yeah. So how do I go back actually? Okay, I'll just start from here. So I already introduced this definition of utility level microgrid. So basically, this is the distribution substation, and then we have 2 feeders. So when we talk about utility level microgrid, normally it includes at least part of the feeder. Now you also see the single customer microgrid that you have here. They can represent like a single household or a facility like Walmart. And the reason that we want to focus on utility level microgrid is because utility is in charge here. So utility is in charge in defining the performance requirements in this type of microgrid, and they are in charge of maintaining that level of system performance in this type of microgrid. Whereas if we talk about a single household microgrid, basically utility will let you run on your own, and you can decide whatever criteria and your satisfaction is your satisfaction, right? So now let's look at just one example microgrid project today. And I take this from the National Grid example where I think I introduced this one in the real world application section, and will not go over it again, but let's look at the requirements that they have for the battery energy storage system in their microgrid. And this language is taken from their RFP, request for proposal, and they listed it on this website. So if you look at their requirement, it requires this black start capability from the inverter or the inverter-based plant. It requires this voltage and frequency regulation of the island, 4-quadrant capable of providing full leading and lagging power factor, and sufficient fault current for fault detection and phase balancing. So if you look at requirements like this, they're helpful for sure, but you may be wondering, like, for example, when you talk about black start capability, what exactly does it mean, right? So that's exactly what motivates us to develop more details and cover more areas in terms of these performance requirements for grid forming inverter-based plant in a microgrid. Now, we believe these are just a few aspects that will need to be defined for grid forming performance, which again includes both steady state definitions such as steady state voltage and frequency requirement, as well as some dynamic requirements on the harmonics, ride through requirement, short-term overload, overcurrent capability, black start capability, and also grounding, etc. So these are just a few aspects that we're considering. Now, I just want to give one example on how we come from the very high level system level performance requirements and then zoom in to see what we need to require for a grid forming plant such that that system level performance requirement can be met. Now, when I say that, I don't mean like just by relying on the grid forming inverter itself, all your system level performance requirements will be met. And one simple example is on a system level, we want the voltage to be maintained within this NC range A, which is basically between 0.95 to 1.05 per unit. Now we want this voltage to be maintained throughout the distribution feeder inside that microgrid. Now, can we rely on the grid forming inverter itself to achieve that? The answer is it depends, right? It depends on the scale of your microgrid. It depends on the location of the grid forming inverter. For example, if the grid forming inverter is located at the feeder head, and now you have a long feeder, what could happen is you will start to have voltage drop along those feeder, and that is not controllable by the grid forming inverter itself. The grid forming inverter can control the voltage locally, but it will not be able to control the voltage throughout the system. So then you need other voltage regulating devices in the system to help to achieve the goal. Now, if you have multiple grid forming inverters throughout the system, then it will help improve that situation as well. Now, besides this voltage range requirements, another important thing when we go to distribution is about voltage balance, or how you handle this unbalanced load, right? Because we have a lot of those in the distribution area. And one thing that is that we need to maintain the voltage unbalance factor on the medium voltage distribution feeder to be below this 3%, which is recommended by the NC limit. Now what we want to find out is, yes, I know this is the system level performance requirement, but then what should I require my grid forming inverter to do such that this can be achieved? So to give an answer for that, we look at a real world microgrid circuit, which is from the Duke microgrid example. And we convert their circuit into PSCAD to run some studies. So we ran several case studies. The difference between them is that, as we can see in the first case, what we require the inverter to do, or the grid forming inverter to do, is to regulate its negative sequence current to 0, which means we don't require the grid forming inverter to contribute negative sequence current in order to balance the negative sequence voltage in the system, but instead we ask it simply to regulate its negative sequence current to 0. And this is actually what's commonly done today in the distribution area for grid following inverter, because standards like 1547 doesn't require anything in terms of negative sequence current injection. So they do it this way, such that when they don't inject negative sequence current, they don't have that 120 Hertz ripple on their DC side, and it actually benefits their design of the DC side capacitor. Now, for case 2 and 3, we then ask the grid forming inverter, instead of injecting 0 negative sequence current, to start inject some negative sequence current with the goal of regulating negative sequence voltage at its RPA to 0. Now, this definition of RPA is the reference point of applicability. We can simply think about it as the PCC of the plant. And the difference between case 2 and 3 is on the negative sequence current capability. So for case 2, we limit the inverter's negative sequence current capability at 0.05. So then based on the need of the system, it can adjust its negative sequence current contribution, but it cannot go above 0.05. Now for case 3, we then increase this amount. Now the current can go up to 0.1. Okay, so now if you look at the results from the simulation and compare all 3 cases, as we can see in case 1, where the grid forming inverter is not regulating the unbalanced voltage at all, the system across the feeder become highly unbalanced, and they are also outside the range of the between 0.05 to between 0.95 to 1.05. And as we start asking the grid forming inverter to regulate the unbalanced voltage and start providing negative sequence current, we can see the voltage imbalance is brought down. And as more negative sequence current capability is granted by the grid forming inverter, we can see the voltage imbalance goes further down. So that gives us the idea that, okay, this table is just to restate what I said using numbers. So as we can see, compare case 1, 2, 3, the voltage imbalance goes down from 9% to 2%, and after the load drop from 19 to 2%. Sure. Mm-hmm. Oh, why it could start? Okay, I'm sorry. Yeah, you can. Oh, here. Yep. Some of the inverters EPRs get disconnected because it's sufficiently long and looking at the time as well. Yeah. What happens when the inverter was disconnected in the system? You are right. If this is a grid following inverter, it would have tripped due to 1547. we did not implement that trip mechanism here because first of all, this is grid forming. And for grid forming, we're not sure whether you need to enlarge that range of operation. And second of all, like the goal of the study is mainly to look at how it affects the voltage imbalance instead of, so the trip behavior will not affect the result much. Okay, so if we think about this study, it basically tells us two things. First of all, in terms of negative sequence, we need to ask the grid forming power plant to maintain balanced voltage at its RPA or to maintain the voltage imbalance sufficiently low at its RPA. Of course, this will be when it operates within the negative sequence current capability and the total current capability, because we can't just ask for a grid forming power plant to do this beyond its physical limit, right? So first of all, we then know we should ask for grid forming in order to do this. Now, second of all, is that enough, right? So if we just ask a grid forming inverter to regulate its voltage imbalance to be 0, for example, at its RPA, without specifying the negative sequence current capability, then the inverter may just have the negative sequence current capability, for example, at a very low value. So that will also not be sufficient, right, based on our study. So we then have this further requirement where we not only ask the grid forming inverter to regulate the RPA voltage to be 0, but also we we also require it to have sufficient negative sequence current capability such that it can regulate the voltage imbalance sufficiently low in all the plausible conditions in the microgrid. And yeah, I'll just walk through this black start capability or black start requirement quickly. Now, as we all know, in microgrid operation, black start is a very important aspect. And the first black start resource should, besides forming the voltage and frequency, then it should be able to sustain the transformer inrush, handling the line charging currents, handling the induction motor starting currents and power. And we all know that a grid forming IBR can be the first start resource, but like Deepak mentioned, not all of them need to be capable of providing such services. So if you have multiple of them in the microgrid, only one of them has to have this capability, but the rest of them may not necessarily do this. Now, on the next two slides, what I want to show is the importance of this grid forming inverter to have the capability to support motor, induction motor startup current, as well as power. And we show this simulation study comparing two cases. For this base case, we have a inverter, a grid forming inverter where its current is capped at 1 per unit, which means it limits its current output to only 1 per unit. Now, if this is the case, then what will happen is in the system is, okay, at this 2 second actually, you start the grid forming inverter and then connect the load on the feeder. So it picks up the constant impedance load. Now, when your motor loads start to start up, you see that voltage dip. And that voltage dip will actually cause the motor to trip, because for motor loads, they have this protection. Whenever the voltage goes below 0.5, it will trip. Okay, so after the motor trips, then your feeder voltage again recovers, and the motor sees this voltage recover. It thinks that the system is back to normal. It tries to reconnect again or to start up again, and the same thing happens. So it repeats itself, but it will never fully get started. And if they do the same thing, but the only difference is we now increase the current limit to 1.6 per unit instead of 1 per unit, we can see now you can successfully start up all the motors in your system. Now, another thing I want to point out is this 1.6 per unit current capability and the power, active and reactive power overloading capability that's associated with it does not have to come from your continuous operating rating of the inverter, because you only need it in this scenario for less than a second, right? So if you have the short-term rating of your inverter, now when I say short-term rating, it means both current rating as well as power rating, because you cannot just provide reactive power without providing active power during that motor start period, right? So if you have this 1.6 short-term rating in terms of power and current, it will be able to black start the motor loads in the microgrid as well. So in a lot of applications today, we see that the battery energy storage system is enlarged in terms of, or oversized in terms of the continuous rating, just to provide black start capability. But also we all know that a lot of inverter manufacturers already have this capability to provide short-term rating, right? So why not we leveraging the short-term rating or short-term capability of the inverters to do this? All right, Deepak.
So the topic of black start, we also have to start to recognize that there can be a possibility of control interactions between the type of load that you have that you're black starting and the inverters in the system. There's one type of interaction that can come up if you're only picking up static load. There's another type of interaction that can come up if you are picking up motor load from a cold load pickup perspective, that all the motors just start up. There's another type of interaction that can come up if the motor loads have a soft start mechanism embedded in them, where the motor slowly ramps up. Now, we looked at this from the perspective of having, let's say you have a feeder, which is, in this case, it is a reduced version of a real feeder, and you're only picking up certain portions of the feeder, and each feeder or each portion of the feeder has probably both three-phase induction motor load, single-phase induction motor load. There's also some amount of industrial load and the same fed by the same substation, which has three-phase induction motor load, which has soft start capability embedded in them. So we wanted to understand that if you're using an inverter for black start and using a grid forming resource for black start, then when you have that three-phase induction motor load for the industrial load that you have, and you have, let's say, some balance of plant load. So think of this as maybe an industrial facility that the main process is run by three-phase induction motors, but you have an HVAC system, you have cooling load present in that industrial facility, you have maybe some lighting load present, which is power electronic, and they all have other kind of characteristics involved in them, and you want to pick up that entire facility itself, what kind of interactions can actually arise? Now, if you have a lot of the load picked up in a staged manner, and if you have maybe a staggered start of the load, then you can probably pick up all the load that is there in that particular facility. But you can also have a scenario where the soft start capability of a three-phase induction motor interacts with single-phase induction motor load. So the single-phase induction motor load that is there as part of, let's say, the HVAC system in that facility is interacting with the power electronic soft start mechanism that's there for the three-phase induction motor load, which is also interacting with the inverter controls that are being used for the black start analysis. So from a steady state perspective, there can be a steady state operating point which can have a successful black start operation. But when you dig down into the real transient operation that can occur in this kind of a black start process, you can have these different kinds of interactions that can come up, which is something that is important to be considered when you're looking at black start from an inverter-based resource perspective. We can probably go about these requirements fast, wherein you have to have the grid forming inverter be capable of providing motor startup current, transformer inrush current, and even pick up some of the local auxiliary load that is there on the network. We'll transition a bit into some of the design considerations that we want to have, and especially looking at from the perspective of, can all types of resources provide grid forming service? How much does the characteristic of the source behind the inverter play a role? We spoke about battery energy storage, we spoke about PV, we spoke about wind. Is there any impact of that source behind the inverter in providing the frequency response characteristic? Do the time constants of the source behind the inverter play a role in the way the resource responds? and the way the system takes that response when it comes in, and do planners have to consider that? So going back to some of the standards, when you look at IEEE 2800 and you think about from the aspect of frequency response being provided, there are default values provided for the amount of reaction time, the amount of rise time, and the amount of settling time, and there are ranges involved. Now, these are only defaults, and the expectation is that if an inverter-based resource can go faster than this, it is expected to go faster than this response time, unless there's an adverse impact on the stability of the network. And this becomes important when we are especially considering things like the ramp rate behavior of a plant. So a battery energy storage system may have the capability to have higher ramp rate as opposed to, let's say, a wind energy storage system because of the mechanical constraints that are involved in the wind energy resource. So taking into consideration that ramp rate capability in providing the service to the system in terms of frequency response is important, especially if you consider the number of resources that are to be involved in this responsive behavior. So consider this network where you have, let's say, an initial strong system where you have inverter-based resources connected in a portion of the network, and you just want to apply a step reduction in the frequency of the network. Now, in this strong traditional system, there's not much impact of a ramp rate restriction or a ramp rate limit, as you see from the response seen here from the active power output of the network, that irrespective of whether you have a 10 per unit per second ramp rate or a 1 per unit per second ramp rate, what you see on the output side, which are these blue and green curves, pretty much a similar response. You do see some restriction of the ramp rate coming into play when you have a 1 per unit per second in the way the reference is generated and the reference is controlled with respect to the ramp. But on the output side, pretty much it's fast. Within 200 milliseconds or 300 milliseconds, you have a settling time of the system for a drop in frequency. Now, the same consideration where in a strong system, this doesn't have an impact. And you can consider this to be, let's say, a battery energy storage system, which is capable of 10 per unit per second versus, let's say, a wind energy system, which is capable of only 1 per unit per second. Now, in a strong system where this doesn't matter or where the ramp rate consideration doesn't play a role, can actually start playing a role in a weak system, or can start playing a role in a system where you suddenly transition to 100% inverter-based resource scenario, wherein if you take that same network and you disconnect that infinite source at time is equal to 2 seconds, essentially creating a 100% inverter system now, if you had a 10 per unit per second ramp rate for these resources, you're still able to maintain stability and able to even pick up load after that. But if you have a slow ramp rate in the response, essentially looking at it from the perspective of not having fast frequency control here. We spoke about fast voltage control in the initial part of the presentation. We're transitioning to fast frequency control, where you now start having limitations on the ramp rate in which the response is provided. What didn't make a difference in a strong system, or what didn't have an impact in a strong system, can actually be unstable in a weak network. And this is where it comes down to what was mentioned of also the time of delivery of service. So if you now, let's say as a planner, if you're looking at this network and trying to procure these various services, it's important to have a notion of how fast can this service be provided, because the burden of providing a service now might have to be split up across multiple resources. So say, for example, you have these resources that can only provide a lower ramp rate of response, 5 per unit per second, as opposed to 10 per unit per second, then you actually need more resources to provide the same service. So the lower ramp rate that you have, the more number of resources you need, because in that unit period of time, you need to be able to deliver the energy into the network. So if you're delivering energy into the network at a slower pace, you need more resources to be able to provide that energy into the network so that the network itself receives the amount of energy that it needs. So if you have only, say in this example where you had 2 PV plants providing 5 per unit per second ramp rate, but let's say for some reason they can each provide only 2 per unit per second, then in order to maintain the same level of stability, you need 3 resources to provide the same kind of stability. So as a planner, if you're trying to now procure these services into the network, you need to start considering the number of resources that are going to be providing the service and the speed at which they are providing the service. And here, although we simplify it in terms of only the ramp rate, it has an inherent implication in terms of the type of resource that's behind the inverter, because its characteristics may translate down into the inverter-based resource. It's possible, yes. Yeah. Yeah. So the time frame in which that energy is to be delivered. Yeah.
Is it fair enough to assume that battery can currently promote the fastest transfer of the converter?
Yeah. Yes.
It's a little bit of a hot button for me, Deepak. I really know where this is going.
Since it's a hot button, Nick, use the mic.
Right, so this is rule of thumb, right? Make it as fast as technically possible. Right? Yeah. No. At least next rule of thumb, you cannot stuff megawatts into a 6-volt.
Oh yeah. Yeah.
Not negotiable.
Yeah.
So gotta get your controls must make voltage healthy before you can stuff the megawatts.
Yeah.
Gotta be healthy, not only where they're being injected, but where they're being delivered to.
Which
So, and that gets lost in this conversation. So just stuff the
no.
megawatts. It's not the right answer. Voltage first, then watts.
That's why the presentation had voltage first, then watts.
You did.
No, yeah, absolutely, Nick. That's true. That you need to be able to first make the voltage healthy, control the voltage, and only then stuff the megawatts. And you cannot just push megawatts anywhere at all as possible, because you just won't be able to deliver that to the system. Yeah. Yes, Lee.
So that means more control with power.
I would say yes, unless, and here it becomes, I don't have it in this presentation, but I'll be talking about it in one of the other presentations in this workshop later on. VAR control usually should have more priority, but there is a caveat there depending upon the type of load that you have. So what we have seen is, depending upon certain type of motor load and how they react to a disturbance, when they are reacting to a disturbance, especially let's say when the fault clears and they're trying to come back, at that point in time, they actually need both real and reactive power. And if you try to prioritize reactive power there or reactive current in that scenario, the motors may actually stall again because the load will drive the motor down. So now in that kind of a scenario, there's not a distinct distinction between prioritizing only reactive current versus active current. You actually need both. Now, how much do you need of each depends upon the type of load and the characteristics of that load. So what we have done essentially there is then not saying that when the inverter is responding, it will hit the absolute current limit for reactive current, which will make the active current go down. So what it would do is it would hit a lower limit for reactive current, which still allows active current to come through and allow that load to not stall or not fall down, but then help maintain the voltage profile and help support the voltage while also feeding active current.
Sorry, another hot button. Just quickly on that to elaborate, right? You can go into it if you accept my earlier rule of thumb, which is amps equals dollars. Yeah, I'm not giving you the option. All right, then you have you can formulate an optimization problem in which you are going to drive the inverter to the maximum amps and pick the angle, the PQ angle for the best recovery. And that work, some of that work has been done in the context of FIDVAR.
Yes.
Fault-induced voltage, delayed voltage recovery, right? So you can come up with it's a great one of these academic exercises because you can do all sorts of great state space stuff to come up with exactly the optimum for the recovery of the machines. Yeah, those concepts have been patented, says Nick, but not commercialized.
Ram will transition and then we'll go. Okay, awesome. Yes, Jason.
Yeah, and I think, just to follow on with what Nick said, I think, having the right speed for the system to be able to accept the caveat of loads and everything is definitely the high priority. But when you look at a different class of resources that have drivetrains versus those that don't, becomes really important as things speed up that you have that drivetrain mode that might interact as well.
Yeah.
And there's a lot of work that is being done right now to understand what is the drivetrain stress, but also the drivetrain interaction and drivetrain oscillations that may occur. And that's a very critical, important part of the modeling and in consideration about these new modes that might pop up because of the drivetrain interaction that may happen, right?
Exactly. Yeah. So then, as we were saying, that you need to first prop up the voltage, you need to help support the voltage. You can't feed megawatts into an unhealthy voltage. So how fast should the voltage control be? Coming back to what we discussed earlier. And what we have found is that we need to, and we don't know if this is going to be generally applied to every system or not, but what we have found that applies to some of our system studies that we have done is that we need to have a step response time at the inverter level of lesser than 1 second. And sometimes it's actually lesser than even half a second. Once we have a closed loop step response time of that voltage control, which is lesser than half a second, then we are able to start transitioning into getting more stable performance in these weak systems. We're probably running out of time, but I think we should be able to complete. So where we transition from this is once we have this kind of characteristics, once we define the performance, once we define the type of behavior, then how do we determine the size of the inverter, or what kind of capacity of grid forming is required? What kind of process should we put into place to determine that kind of capacity of the inverter? And because there are similar characteristics with respect to these different grid forming control types, we can use, at least for a initial calculation or initial study, we can start using generic representations. And this is, of course, from a long-term planning study perspective. As you start getting more during commissioning time, it's obviously more recommended to have more detailed information from the manufacturer, get more information in the type of control, the type of models, maybe black box models, and so on. But if you look at it from a planning perspective and utilize generic models, we can have both time domain and small signal stability characteristics in order to identify the capacity of the grid forming resource that is needed. And this also leads towards one of the points that we previously had, that it depends upon the location and the sequence in which you're installing these grid forming inverters. So take this example where you have an existing system. If you have, let's say, 3 inverters which have all grid following characteristics for now, and you isolate this system, right? So the goal is to try to create a small signal disturbance, because we don't want to really look at large signal perspective for now. But supposing you create a small signal situation where you isolate the system equivalent, then the amount of flow to the system equivalent is very nominal, right? It's around 1 megawatt, 2 megawatts, half a megawatt, 2 megawatts. But if now all of these inverters are grid following in characteristic, then you can create a small signal representation and really find out that all of these inverters will go unstable, or the system itself will go unstable, even for as small as a disturbance of just half a megawatt and 2 megawatt, where one would think that, okay, maybe it will settle down, maybe it will settle to a new operating point and so on. But in reality, if these are all grid following and they have aggressive controls and so on, you can create a small signal profile to showcase that it is unstable. And we found out from the participation factors and so on that it is the reactive power control mode that is driving the instability in all of this. And here is where it comes down to, when do you start bringing in grid forming, and what are the implications of not bringing in grid forming as soon as possible, at least from a fast voltage control, fast frequency control perspective. So if you change just one of those inverters to grid forming in the existing system, you can make the system stable. From a small signal perspective, from a large signal perspective, you can make the system stable. So the implication here is, let's say you have a interconnection request, you have an interconnection queue coming in, and as Nilesh mentioned, you have, let's say, a resource coming in that wants to be grid forming, but you say that you do your analysis and find out that in that particular location, maybe grid following may be better, because in that particular location, it's not providing enough service, or it's not providing enough incremental benefit and so on. There could be consequences of that in the future. in terms of once you have more grid following resources placed, the size of the grid forming inverter that you need to further stabilize the system later on could actually increase. And what that has is, as an implication, is maybe after a point, the cost to put that next grid forming inverter could be larger than what you could have put before. So in this particular case, if you change one of the existing inverters, or let's say you had an interconnection request come in for one of the inverters and decided that it can be grid following, the next inverter that you need to be grid forming would have to be much larger size than if you had changed this inverter itself to be grid forming to begin with. But of course, making these decisions requires more analysis, requires more forms of stability analysis and so on, which we don't have much of the time to go into the details here. And here is the example that in order to, if you kept all inverters as grid following, you needed a new 150 MVA inverter to make the system stable over and above the 3 grid following inverters that you had. But if you had just changed one of those inverters to grid forming previously, you could have made the system stable. And if you did not have, let's say you're a planner and you did not have any new inverters coming into that portion of the network, then as a transmission network provider, you might have to put in an asset to become grid forming in that space, which means there's an additional cost consideration there. So moving, like what Andrew said, let's start getting grid forming technology as soon as possible with the aspect about fast voltage control and fast frequency control. And the last section that I have, if you don't mind staying for 5 more minutes, is how do we plan a network with grid forming? And what kind of metrics can we use in order to understand what size of grid forming inverter to be placed? Is this the right location to place grid forming? Can we have simplistic metrics that could give us an idea, take us 80% of the way? So the previous slides showed actually more small signal stability analysis and the entire gamut of stability aspects that are there, but can we really get something even from traditional planning metrics if you look at a wide system as a whole? And can we utilize generic models in order to do that? So we've been looking at 2 different types of generic models, wherein we have both single loop and multi-loop controls of grid forming inverters located in it. It can cater to a wide variety of grid forming technology, the types that we spoke about previously in the presentation. This is just an example of the types of models that we have. And where we can utilize now these models to start planning the system is if you consider a network like this, wherein you want to try to understand how to locate grid forming inverters, how to size them, and you want simplistic rules of thumb to get 80% of the way. And you want to see that, supposing you have an existing number of synchronous condensers. So the objective that we wanted to study here was that you have synchronous condensers in the network, but you want to retire them, or you no longer want to keep synchronous condensers and you want to replace them with grid forming inverters. Then how do you utilize the kinds of metrics that you have available in order to understand where to place them? And one of the things that we used was to essentially identify if you can place the grid forming inverters or not, is to try to understand the stability of the network, both in EMT domain and positive sequence domain, with the appropriately parameterized models. And we found out that firstly, the network is unstable when you start retiring synchronous condensers. So it shows the need that you have to start using these advanced technology types. And secondly, you can use metrics both, just it's not a direct linear relationship, but you can use both the short circuit capacity and the MVA available. So you can evaluate the remaining amount of MVA that is available at that particular node in the transmission network. You can utilize the value of MVA availability or the remaining MVA availability, especially where it starts becoming negative, to try to get a baseline to size your grid forming inverter. So you can find out at which bus the MVA availability is becoming negative. You can then use that as a planning criteria to try to get a minimum size of a grid forming inverter that is needed to be placed at that particular location. And once you utilize that, as you start increasing the size of the grid forming inverter, you can push the MVA availability to a positive value, and then you can get a stable response. So it's a initial planning process to start looking at the location for grid forming, looking at the size of grid forming that's needed. And here in this example, we could replace 150 MVA of synchronous condensers with 80 MVA of grid forming inverters. So the size of the grid forming device that's needed to stabilize the network with the synchronous condenser retirement was much smaller than the MVA rating of the synchronous condenser itself. And I think all the implications we have really covered, but I think the main thing we wanted to cover or get the message across was that we need to start getting grid forming inverters into the system, but we don't want to focus on the control type, rather focus on the performance that's required, the services that are required to be provided by those inverters, and let the manufacturers choose what kind of control type they want to implement, as long as they can deliver the service that is asked for and that is required. But as we get more of these inverters, there's going to be an added emphasis on doing more detailed studies in multiple simulation domains. Multiple analysis needs to be carried out to understand how these inverters would interact with each other, what kinds of new modes might come up, what kind of new stability criteria might come up. And that will just require more and more studies and analysis to be done with improved models and techniques. And it should not be a silver bullet. There are so many different solutions out there. You can't throw grid forming at every problem that is there. After a point, you just maybe can't transfer power over a transfer capability path, right? So you have transfer capability limitations, which grid forming inverters may not be able to solve. So there are multiple solutions that we need to explore in order to have more inverters in the system and respect the physical limits of the inverter. And just like how you can have instability with traditional inverters, a grid forming inverter can also have stability considerations. It can also have instability. So it's not a guaranteed fix that just because there is a grid forming inverter, everything will be stable and everything will be fine in the system. A grid forming inverter also needs to have tuning rules. It also needs to be designed properly and so on. And with that, we come to the end. So thank you for your attention and all the questions.